Hi, everyone. Welcome to the second talk by Professor Konstantinos Zoubos from the University of Pretoria. Zoubos completed his PhD studies at Stony Brook, New York in 2004. After postdoctoral appointments at Queen Mary, University of London, and the Niels Bohr Institute in Copenhagen, he joined the physics department at the University of Pretoria in 2013. His research focuses on several aspects of high-energy theoretical physics, such as the ADS-CFT correspondence, integrability in gauge theory, and mathematical structures such as quantum groups. Last week, he gave us an introduction to spin chains and supersymmetric gauge theory, and now he will talk about spin chains from quiver gauge theory. And now I hand over to Professor Zoubos.
Okay, thank you so much. I'm delighted to be back for the second talk in the series, and I'll be giving a more standard slides presentation this time, but if there are questions, please stop me, and I do have a notepad in the background that I can scribble on in case I need to answer something, so don't hesitate to ask. So what I wanted to talk about today is some of the stuff that's occupying my time and interest at the moment, and in particular, how some of these ideas I discussed last week about how integrability can arise from gauge theory can be extended to a less supersymmetric context of n equals 2 quiver theories, which I will introduce and explain. And unfortunately, it will turn out that I won't be able to say all that much about, I'll say a lot about spin chains, but I won't be able to say all that much about integrability because a lot is still to be understood about these quiver theories and their corresponding integrable properties. So I'll take some small steps in this seminar and talk about the symmetries first and a better understanding of those, which might eventually lead to a better understanding of integrability. So some of what I was talking about last week about how you understand integrability is, at least so far, not applicable in these kinds of theories. I'll explain some of the reasons why. So this is work based on ongoing collaboration with Eli Pomoni, who is based at DESY in Hamburg. And the first paper was with Randall Rabi, who was my student. And this one, the latest one to appear was with Eli's student and one postdoc at DESY, Hanno Bertle and Xinyu Zhang. And I'll briefly touch upon some work with Jared, which I believe you all know, which we hope to appear in the coming month or so. All right, so let's see what we're going to be dealing with today. So I'll have to introduce a new concept that was not there last week, which is the orbifolds of n equals 4 super Yang-Mills theory, and discuss the spin change we get in the planar limit from these kinds of orbifolds. And after I kind of say a few things about the spin change, I will move on to, I'll switch gears quite a bit and talk about something which we'll call groupoid symmetries. So I'll be generalizing the notion of Lie groups to the appropriate context that we need to understand these the symmetries of these theories. And then I'll say something about twisting away from the orbifold point, and then summarize a little bit what we are thinking about at the moment. All right, so the n equals 4 theory, I discussed it already last week. So here are some of its main properties as a reminder. It's a unique theory if you want in 4 dimensions, the theory that has the maximal amount of supersymmetry, so the maximal symmetry between bosons and fermions. And it contains a gauge field, so it's a gauge theory. It has 4 spinors and 3 complex scalars, which I spent some time with last time. And they're all n by n matrices, meaning that they live in the adjoint of an SUN gauge group. I'm not going to really need the superspace notation. This is just for completeness here. Somehow it's convenient for supersymmetric theories to have to pack all one's fields into a bosonic but chiral superfield, which contains both the bosonic and the fermionic fields in one field, and some auxiliary fields as well. You don't need to know much about this notation. I'm not going to really need it, but this allows us to write this function here, the superpotential, which you can see for n equals 4 takes this very simple form, x computed with y and z, where these are the superfields, but you can think of them as just the scalar fields, the complex scalar fields, x, y, and z. And the potential itself is just the square of this. So you take the derivative with respect to one of the fields and square it, and I wrote this expression down last week. What I want to focus on now a little bit is the symmetry. So what are the explicit symmetries of an expression like this? Well, it's easier to write it instead of the commutator to write it as in this expression. So as an epsilon tensor, the antisymmetric tensor times a trace of the three fields where I, j, and k are just the indices labeling these x, y, z's. And now you can immediately see that there's an SU3 symmetry here, because epsilon ijk is an invariant tensor of SU3. So if I transform under SU3, then I'm going to get the determinant of SU3, which is 1, and coming out, and that shows invariance under SU3. There's also a U1, which has to do, which you cannot see it here, it's an internal symmetry of the superfield. So you can rotate the fields within the superfield, and it's not so visible from this picture here. But there's also an extra U1 that you can see explicitly in this superspace notation. However, this is not all. Actually, there is more symmetry in this theory, because actually this was only for the holomorphic fields. So x, y, z were the holomorphic fields. You also have the anti-holomorphic ones, so they're Hermitian conjugates. And you can pack all of them together into an SU4 representation, which turns out to be the 6, the antisymmetric representation of SU4. And you can show, this is the action of SU4 on these fields in this notation here. Okay, I'm giving some examples, like some generators take a z to an x to a z. You can think of this as some SU2 inside SU4. Some of them do other things. They can take a z to a y bar, a z to an x bar, but you can kind of think of each couple of generators can correspond to a specific SU2 within the SU4. And the claim is that this action, action of SU4 leaves this Lagrangian, the full Lagrangian with the kinetic terms and the superpotential invariant. Okay. Now we're going to move away from n equals 4. Okay, that's a known story. People have been working a lot with n equals 4 over the past 20 years in the integrability context. So to move away and go to n equals 2 supersymmetry, we'll take this theory, but now increase the gauge group to SU2n. So now we have 2n by 2n matrices. Still the same scalar fields, still the same SU4. But now I'm going to do a projection. So in this space where these fields live, the x, y, and z, we call it the R symmetry space, because there's this SU3 which relates them, this SU3 R symmetry, which rotates x, y, and z. I'm going to do this projection where x and y become minus themselves, but I leave z alone. So basically, I'm choosing an SU2 given by x and y as a doublet, and I'm minusing that one, while at the same time, z is a singlet under this transformation. At the same time, I'm projecting in color space. So these are all 2n by 2n matrices, and I'm doing this projection where, well, here I'm doing a conjugation, I'm transforming, so that with this matrix here, I and minus I, n by n blocks. And then I'm asking that the combined product of these two operations, so x to minus x, y to minus y, and at the same time multiplying from the left and right of this matrix, is invariant. And what that does, it actually kills essentially half of the components of each field. So if you think of this Z, then it used to be a 2n by 2n matrix, but now asking for this invariance actually gives you this n by n times n by n block. And the same for the x, but just now the n by n blocks are not sitting diagonally, they're sitting off diagonally, because at the same time you have this minus here. So this is a very important operation. This is a very important set of equations for the rest of the talk, because it introduces our main players in this game, which are going to be the Z fields, which are adjoint, but now they're adjoint of two different gauge groups, because these are the remaining gauge groups in the picture, and X and Y are bifundamentals. What that means is that this X12 lives in the fundamental representation of the first SU2 and the anti-fundamental of the second SU2, and the opposite for this other X. So we have increased the number of fields in a sense, kind of artificially, you could say, because we're just getting them by projecting a 2n by 2n set of fields. But as you'll see, this will introduce a kind of a different type of behavior for our gauge theory. So the way to represent this and kind of to remember where everything goes is to use this a picture here called a quiver diagram. So I guess quiver originally comes because quivers are what you put arrows inside, and quiver diagrams are defined by arrows. So here I'm labeling by 1 and 2 the two different gauge groups. So recall we have two gauge groups here. It's not a single gauge group here. Now I have two different gauge groups. So I'm labeling by 1 and 2, and blue and red as the just to distinguish the colors if needed. And we can label by arrows where which kind of fields are charged under which SUN gauge group. So this means that Z1 is fully charged under the first gauge group, meaning it's in the adjoint. So it has one upper and one lower index, or one fundamental and one anti-fundamental of the same gauge group. These ones go between the two gauge groups. You can write on the superpotential. Now it looks a little bit more complicated. And naively, and that's going to be important in the second part of my talk, this SU4 symmetry that I wrote earlier is actually broken to a subgroup, an SU2 times SU2 times U1, because, for instance, we used to have an operation where a Z, I wrote it earlier, a Z became an X, or an X became a Z, right? I wrote that for the n=4 theory. But here, notice that this operation wants to take something which is the adjoint of this gauge group to something which is the bifundamental of these two gauge groups. So the gauge indices do not match. So this is definitely not a gauge invariant operation that one wants to define here. And that's why these generators, which are the ones not belonging in this subgroup of SU4, are broken or naively broken. I'm going to revisit, of course, this statement. That's kind of the point of the talk, to revisit the statement and see whether we can actually improve on this statement and regenerate these generators and make them actually valid for these orbifold theories. Are there any questions at this point about what the main theory I'm going to be looking at is? Okay, so now, of course, you can play the same game as for n=4. So you can, okay, one thing before, you can also, of course, here, you see that we have a coupling, well, we have two traces. One has to do with gauge group 2, the other one with gauge group 1. And these couplings are equal in the way you obtain them from n=4, but you can actually also consider deforming away by making these couplings of gauge group 1, gauge group 2 unequal. And that's what I'm saying here. You can move away from what we call the orbifold point and have this more general superpotential. And it's kind of a non-trivial statement that when you do that, n=2 supersymmetry is actually still preserved. So we've broken n=4 to n=2 because we kind of did this identifications which treated the x and y's differently from the z's and the v's. V is the gauge field, so that broke the n=4 supersymmetry. But this preserves n=2, and it gives you kind of interesting spin change, and that's what I'm going to focus on for the next, let's say, 10 minutes, in again, the planar limit. So you can repeat the same story as n=4, where we discussed last time that you can look at gauge invariant operators and look at their, so maybe I can quickly also remind you from the previous talk. So what we did, so I was looking at gauge invariant operators like this and mapping it to a spin chain and then seeing what's the eigenvalue of the one loop dilatation operator on these gauge invariant operators, and finding that it corresponded to a Heisenberg spin chain Hamiltonian. So now we're going to look at this picture and try to improve on it or generalize it to this case where now I'm talking about these these fields are not the fields of n=4 anymore. They're going to be the fields of the Z2 quiver theory.
So this is your main motivation for being interested in this reduction, because you see those spin chains and you want to use them as tools.
Yes, well, okay. I guess my main motivation is more, I think I gave it at the end of last time that okay, n=4 is beautiful and we have all this integrability, it's very powerful. We have these Y systems and you can solve the Conici operator. Can you do anything like that for less supersymmetry? with a view, I think I was asked that question last time, with a view of going to more realistic theories and, maybe,
But this is
the end of the.
This is a convenient tool for you to invest. Right? That.
Yes. So I would like to be able to have integrability ideally, or some version of integrability that I would be able to. So I'm studying the spin chains, not because I necessarily care about this particular spin chains, although as I will say, they're actually quite interesting by themselves. And some of them have interesting also condensed matter motivations that you could probably be interested in without caring about the gauge theory. But for me, it's more, I want to learn the behavior of the spin chains in order to make some progress with the gauge theory, like the spectrum of the gauge theory.
All right.
Yeah. But you see now, compared to before, there's a little bit of a difference, because the X and the Y fields, and again, I'll go back to this picture, you see the X and the Y fields here, they are, there's a complete SU2 symmetry between them, like X12 can be mapped to a Y12 and backwards. That does not break any, this SU2 symmetry that was there, the X and the Y doublet, but the Z and the X are, of course, now in very different representations of the gauge groups. So it's still worth studying, but, it's not going to be an SU2 doublet that they make up, and we need to understand how that affects things. Okay, this revises a little bit the discussion from, reviews the discussion from last week. So in the planar limit, as we discussed, you can write observables as gauge invariant operators. And if you want to diagonalize the dilatation operator, then you identify D with the Heisenberg Hamiltonian, and you use integrability to solve the spectral problem. That's what in one slide, what I spent a little bit of time last week to explain. So our goal eventually is to find these gammas, which are the anomalous dimensions. The one loop anomalous dimension. And now we can do diagrams. So for instance, these are Feynman diagrams, which are, and again, maybe this should be explained a little bit better. What does this diagram mean? Let me take an operator. So think of an operator, a gauge invariant operator, which I can think like that. So there's an X, let's say 1, 2. Now by gauge invariance, the next field has to be, if this one ends with a 2, the next one needs to start with a 1, because these are in the same chain. So X1, 2, Y 2, 1. Maybe there's a Z1. These are the fields we're building in this case. Y1, 2 again, maybe something like this. And now we want to take this and take the conjugate operator, or a set of operators containing the conjugate quantum numbers of these ones, and we want to first at tree level write down this this correlation function, so O of X, O bar of Y. So this O bar, this is O at X. And in this simple sector that we are looking at because I'm looking at the holomorphic fields, if you want to do this, okay, this is the tree level weak contraction between the X's and the corresponding X bars and Y bars and so on. The first one loop correction comes because there is a quartic vertex in the theory, and that is going to give us something like this. So this goes like that, this goes like that, and you have a quartic vertex, and you have a one loop. Okay, so this is the one loop diagram that you need to calculate. These are very simple diagrams in these theories. This, of course, these are all the same point. This X and this is Y. These are simple diagrams in general to calculate. They are divergent, as I said, so you need to do some regularization. I'm not going to be focusing on that because they're all the same for all these kind of scalar Feynman diagrams. But I'll just focus on the on how they look with respect to the gauge indices. So the gauge indices here are blue means gauge group 1, dotted red means gauge group 2, as you can see. So 2 follows this line, 1 follows this line. And in the deformed theory, these will have also different coupling constant dependence. So this quartic coupling can be either a G1 or a G2 squared, depending on the gauge group. So these are actually the only contributions in this XY sector that we really care about at this point. And if you rescale by, say, some overall G1, G2, then what you get is this planar Hamiltonian, or this Hamiltonian at a planar level, which acts on this basis. So these are all the possible combinations of fields in this basis. and in this sector, and this is the Hamiltonian, which you can also write in a more what we call dynamical way by indicating what the first index. So you see this block has first index 1, and this block has first index 2. Again, I remind you what the index is. The index means that it's charged under the first gauge group, and I call that by 1. I could have put explicit, if I wanted, I could have put explicit gauge group indices like A, B, and then maybe A hat and B hat for the second gauge group. But to avoid unnecessary notation, I'm just calling it 1 and 2. And so the Hamiltonian here looks like this. And you can see that the Hamiltonian acting on fields that start with 1, so this upper block looks like this. And this up to a rescaling by kappa is just simply the Heisenberg Hamiltonian. So again, maybe looking back at last week, that's how I started the discussion. And we had the Heisenberg Hamiltonian was this. Okay, there was a factor of 4, but this is the Hamiltonian. Here, the 4 has been rescaled away when I took out the couplings, the G1 and the G2, but I get this ratio of the couplings, kappa. Okay, and here I also do the same for gauge group 2 being first, but now the ratio of the coupling is not 1/kappa, it's actually kappa. And that's because these diagrams depend on different coupling constants. That's something obviously that you cannot do for n equals 4 because there's only one gauge group, one coupling constant. Now you have 2. So if I go to the XZ sector, which is the one that has a bit less symmetry, but actually things don't look very different. You can still do these kind of diagrams. You see now you have Z's, are either fully blue or fully red, right? But they can interact with the X's. There's also a YZ sector where instead of X's I have Y. I'm not going to look at that sector because it's exactly equivalent to this XZ sector. So I'm going to only look at this XY and XZ. And here the Hamiltonian is similar, but also different, where the kappas appears in a slightly different location than in the previous XY sector. So again, the basis is where here I'm writing the block where the first index is 1, and with a 2 here, I'm in the block with the first index 2. And for those of you who've seen these things, this looks quite a bit like a temporary leap type Hamiltonian, which appears, let's say, in the XXZ model. But it's not really that because it's dynamical, meaning that it hops between H1 and H2 between different sites, depending on whether you are even or odd. Or depending on whether basically your X or your Z you're acting on is a 1 or a 2. To make it more clear, let me illustrate the spin chains like this. So the XY chain, because every time you cross either an X or a Y in your chain, and again, maybe that's something I need to write. So if you have, let's say, an X12, X21, Y12, X21, and so on, this is your chain. Well, here the gauge group is always, the first gauge group is always 1. Here the first gauge group is always 2. Here it's always 1. So you see that you're just exchanging gauge groups as you proceed with your gauge invariant operator. And in this sector. While in the XZ sector, if you have an X12, then you have, say, a string of Zs. These are all going to be Z2s. Because these are all, or in this of the second gauge group. Only when you get another X do you eventually now flip to a gauge group 1 so that this is a Z1. So they behave quite different. This is purely alternating, and that's what I'm drawing here, where on this is a red, so that's gauge group 2. So you have H2 acting on it. This is blue, that's gauge group 1. And you alternate the Hamiltonian. Well, here, this is a much more dynamical kind of chain where, by dynamical, we mean that the Hamiltonian is not fixed at a given site of the chain. It is dynamically determined by the configuration of the chain. So so the number of Zs in particular you have crossed before you get to a particular site determines, or sorry, the number of X's you have crossed determines what the Hamiltonian is. So here, whether this Hamiltonian is H1 or H2 depends on how many X's have crossed at each site. And of course, for different configurations, you can have a different number of X's. So you cannot tell me in advance what the Hamiltonian is going to be. Here I introduce something known as a dynamical parameter, which takes two values. And what I mean by this is that, h lambda is h1, h lambda prime is h2. There are good reasons to make this into a parameter rather than just calling it 1 and 2. But I'm not really going to go into that in detail in this talk. But the whole point is lambda just gets exchanged when you cross an x or a y, or does not change when you cross a z. Okay, so these are kind of some funny and somehow slightly unusual spin chains, definitely this dynamical one. For the alternating chain, it's actually not too unusual. There is condensed matter literature on these types of chains, although mostly they care about the antiferromagnetic case. Order or not in that case. Here, of course, we have a ferromagnetic case. But there are some examples of ferromagnetic cases. One of them is this kind of bimetallic manganese, I think a nickel case, where what actually alternates here is not the couplings at each site, but the spins. So here you have something which is spin 3/2. I think this is spin 1, 3/2, spin 1. But mathematically, the way you would study such a chain and like diagonalize it is exactly the same as our two coupling chain. So it's not, these are not totally somehow irrelevant chains for real applications. People have studied these kinds of chains because they do appear in some generalizations of ferromagnetic systems. And even though there's many techniques, many approximate techniques that have been used, like long wavelength and this recursion method, which is a very powerful method that applies to these kinds of chains, it's not really known yet whether these kinds of chains with alternating couplings or alternating spins are integrable. So that was one of our motivations, to see, well, how far can we get with these spin chains, even if they're not integrable. Of course, integrability, we actually prefer it in a sense to be broken at some point because real life is not integrable. But can we still use techniques such as these ones that have been used here for studying, studying this spin chain and finding the spectrum corresponds one-to-one to the spectrum of the gauge theory. So to the anomalous dimensions of the gauge theory. So it's a very interesting question whether we can study them in this way. Are there any questions about this before I move on? Just to say that, okay, then that recently with Jared, as I mentioned in the beginning, we've been looking at even more general cases of orbifolds. So a particular case is the D4, affine D4 orbifold, where you take another subgroup of SU2. Z2 was just a special case. It's the simplest possible subgroup of SU2 that I orbifolded with. There are more general and particular non-abelian subgroups of SU2, just as this one. And this gives you a situation, a quiver, with 5 gauge groups. So there are 5 nodes and 13 fields in all that you can have here. So there are the Zs, which go from one node to the same, and the Xs that are bifundamental under different nodes. And I'm not going to really go into all the details of how we got this, but one can write down the potential for this, and you can write down the Hamiltonian. And it has kind of some interesting properties, this Hamiltonian, which is that, as you write down fields along your gauge of an operator, as you have magnons that are moving, either they can get reflected, but when they get reflected, they get a factor of the corresponding coupling constant, if it's a 1 or a 2 and so on. Or if they meet at one of the nodes, so if an Y51 and X15 meets, then you get a much more complicated combination of things that are kind of coming out. So they can scatter the same way, or they're going to get exchanged. You can see here a Y and an X got exchanged to an X and a Y. So it has quite an interesting pattern of scattering, and we've been studying that with Jared in particular. For instance, just as an example, there are 4 ratios of couplings. I think I mentioned that here. You can write 4 ratios of, let's say, GIs over G5 that you can have. And of course, there's many ways to deform away from the orbifold point. So this is just one particular one, okay, just to show something. And if you look at the holomorphic sector with length 3 sites, then you get at k equals 0 is the orbifold point. So that's where this is known to be integrable. There have been studies that shows that the orbifold point is integrable. Now we want to move away. And you can see that there's a very interesting pattern of how the spectrum of the theory of the spin chain gets deformed as you move away. And of course, this tells us something about the gauge theory. There are some states which are here. You cannot see them very well, probably, but they're in blue. These have zero energy. These are known as BPS states. In gauge theory, these have do not take anomalous dimensions. This red one is the superpotential, which is this operator here. So this operator starts off with a dimension of 12, anomalous dimension of 12, and then you can see that that increases. But there's also these other operators which are interesting also, and we are trying to kind of decipher a little bit their structure and also obtain this from a Bethe-Ansatz, because this is just explicit diagonalization, just putting this in a computer and just finding the spectrum, which I can do for length 3, I can do for length 4, but it becomes, of course, very, very difficult as you increase the length. There's many more states. It's a computationally very hard problem, while, of course, what we're hoping to do is to be able to use techniques like the Bethe-Ansatz to get these, bypassing the need to do it by brute force. So we are trying to check, let's say, these results from the 2 Magnum Bethe-Ansatz and see that, and that is kind of known, it's going to work. There's no mystery here. 2 Magnums, you can always do a coordinate Bethe-Ansatz. Integrability only starts kicking in when you want 3 Magnons. This is related to what we were discussing again last time with, when I was discussing the Yang-Baxter equation. I think I had it somewhere here. So for 2 sides, you can always write a Bethe-Ansatz similar to this one and kind of solve your problem for any kind of, at least the spin chains I know of. But if you wanted to work at 3 sides, so for 3 Magnons, then you need really the Yang-Baxter equation to make it work. And here, as far as we are aware, we don't have a Yang-Baxter equation. So we need, of course, we want to study that. That's kind of the eventual goal. But as a first check of our formalism, we're going to do the 2 Magnum case and just confirm that everything is, and that's already contains quite a lot of information, of course. It's quite interesting, but going to 3 Magnons might be a little bit more tricky. I'll come back to that at the end, because even for the Z2 case, the XY sector, at least, no, the XZ sector, so this kind of sector that is here, there has been recent progress in going to the 3 Magnum, 4 Magnum Bethe-Ansatz, even though integrability is still perhaps not really there. But my colleague Ellie Pomoni and her students have managed to actually solve the 3 Magnum, 4 Magnum case with some assumptions and all that. So maybe there is hope that one can do more than just the 2 Magnums here. All right, I think that's all I wanted to say about just talking about the overall spin chains. Now I want to switch gears to the symmetries. So is there perhaps a question about this D4 case or the Z2 case I was talking about earlier before I move on?
I have a few questions.
Yeah.
The first is, okay, so in the classical case, if I'm testing for integrability, I know I can use something like a pain lift test to, as kind of a, necessary but insufficient condition to test for integrability. In the quantum case, what do you have?
Yeah, that's a good question. I mean, of course, the pain-Levé and all that, that's ODEs, right? And so, so it's a much simpler context, right, in general. So if I would say that even for classical field theory contexts, so where you have complicated PDEs, I'm not aware of like a very simple test. I mean, what you have to do is numerically run your system and see if you see chaos, as an example. So if you see chaotic behavior in your system, I mean, it's not a proof of anything, but it's a very good indication that you don't have integrability. And there are some techniques that reduce the PDE to an ODE, where you can use some analytic non-integrability techniques, which at the end of the line come down to, well, it's differential Galois theory and all that, but in the end they come down to, ODE type tests. Here for the quantum case, there are, so you can simulate your spin chain, and you can look at the spectrum of eigenvalues. And in that case, the main question is, does your spectrum follow some kind of random matrix model, like some Wigner type distribution, or is it much more Poissonian? Like, you look at the distribution of your eigenvalues, but you have to have quite a few, of course. You have to go to higher lengths to have more states. And that typically gives you a good indication whether you have quantum chaos or not. So basically, the type of distribution that you get from your for your spectrum. If you don't want to do it computationally and you want to do it analytically, which is more or less what we are trying to do, I guess then you need to have some kind of Yang-Baxter equation. So that is your ultimate test. If I can write down an R matrix which satisfies the Yang-Baxter equation, or some simple generalization of the Yang-Baxter equation, there's something called the dynamical Yang-Baxter equation. So if I can find an R matrix which satisfies an equation like this and gives me the Hamiltonian in a particular limit of the spectral parameter, then I'm done. Then I know we have integrability. Of course, if I don't find one, I mean, it's not clear because there are many complicated R matrices out there that don't have simple properties like a difference property for the spectral parameters and so on. So I'm not sure if you can really, I mean, maybe for small Hilbert spaces, like if you're working only with 2 states at each site and so on, maybe it's possible to do an exhaustive search for R matrices. And if your theory does not fall into one of those, then you can argue that it's not integrable. We are not there in this theory yet. I mean, our Hilbert space is a bit too complicated compared to just an SU2 because it's this dynamical SU2. So we don't really have any proofs of whether, like general proofs, whether there exists or not an R matrix that gives us the correct Hamiltonian and satisfies the Yang-Baxter equation. That would be very welcome, of course, if somebody can do that. But until we have that, then, well, that's kind of the goal, what I'm going to talk about now. If we are to ever make some progress here, we need to understand the symmetries better, is going to be my punchline. And I'm claiming we still have a lot to do in terms of understanding the symmetries for these theories before you can write down an R matrix and then check for integrability.
Okay, thanks. That's very insightful.
Okay. Any more questions or should I move on?
Hi.
Hello?
Hi. Yeah, so I wanted to ask, so you mentioned that if you stay on the orbifold point, then you know that your theory is integrable, and so is there, is it just the theory at that point that's integrable and like nothing around it, or is there some structure to the way you deform these theories where you say, okay, if I carefully deform, perhaps I can keep much, if not all, of the structure without?
Yeah, so we are letting, okay, so of course, if you start with the orbifold point, which is here in this case, k equals 0, or kappa equals 1, let's say in this Z2 case, first of all, one thing I should say is that it's known to be integrable because people have done the one loop computations and they have compared them to one loop Bethe answers that you can write down. But it has not been proved, the integrability of the orbifold has not been proved by standard techniques. And what I mean standard is, for these kinds of systems, you need a Yangian. There is a generalization of your symmetry group called the Yangian, an infinite-dimensional group, which underlies integrability of the XXX model. People have not, as far as I'm aware, written that down for the Z2 or the T4 or even less theory at the orbifold point. So that is still something that somebody needs to work out. I mean, it's going to work, it's going to be there, but it might look a little bit different from the standard Yangians. Okay, so that's one point. Now, if you wanted to start with the orbifold point and move away in a way that is integrable, you can do that. There are several kinds of twists, like beta deformations and all that you can do. However, these are not well motivated by the gauge theory. So here, our motivation is purely gauge theory. So we want to start with a gauge theory and deform it in a way that preserves n equals 2 supersymmetry. And so that's our main motivation. N equals 2 supersymmetry has to be preserved. I could deform in a way that breaks n equals 2 supersymmetry, but that might somehow be integrable, but it would not be motivated well from the gauge theory side. Like there would not be a corresponding gauge theory, really. I mean, I don't care about specifically deforming the integrable structure of the orbifold point per se. I want to understand our specific n equals 2 theories, what is their integrable structure, if there is any. So I'm not sure if I'm making that distinction clear.
Yeah. I think it's clear.
So for instance, the thing you can do for any SU2 chain is like the Heisenberg, you can do an SUQ2 chain, so deform to the SUQ2 symmetry, the quantum group. That is the symmetry of the XXZ model with appropriate boundary conditions. So it's natural to say, why don't you just take Heisenberg and deform to XXZ, right? But that is not very well motivated from the Gates theory side. Like there's nothing you can do specifically to the Gates theory side that preserves some supersymmetry and gives you XXZ as your Hamiltonian. So we're not really interested in XXZ in this context. Of course, XXZ is interested in many contexts, but not. So in this one, I don't really know whether any of the standard quantum group deformations that you can do are relevant to this game. So we're kind of playing a new game because we're following the physics and not so much the integrability.
Okay. I think I understand. Thank you.
Okay, great. Thanks. All right. So, okay, I'm aware that my time is running low, so I'll probably kind of skip a few things from now on. But I think it was important for me that at least to understand what is the general playing field that we're working with. And now let's start a little bit on the orbifold point. And again, I probably won't finish everything I want to say, but that's definitely fine. So this is what we published at the end of last year, where we tried to understand, let's say in the Z2 quiver theory, how do you generalize this statement that SU4 is broken to these two SU2s and kind of revive these broken generators? Our claim in the end was we can upgrade these generators. So R13, R14, 23, 24 are the ones which used to be there in SU4, but now they have an index of this unbroken SU2 and an index of this other unbroken SU2. But they are definitely relating fields, as you can see here, with different gauge indices. So this is an adjoint. So I and J live in the same gauge group. This is a bifundamental. I and J hat live in gauge group 1 and gauge group 2. So we want to be able to write relations like these and make sense of them, even though they look horribly non-gauge invariant. Right? So we need to be able to act consistently on this. And okay, why are we doing this? Is it just something we woke up one morning and decided, okay, this has to exist? Well, the overall picture here that we're trying to build is that when you are taking orbifolds, you, especially in terms of integrability structure, you're not really breaking your original SU4 symmetry. You're just deforming it in a particular way. And if you understand that deformation of the SU4 well enough, it's going to be a quantum group deformation, of course, of SU4. If you understand it well enough, then you might be able to move on with integrability. Okay, so we don't want to really classify all possible symmetries here. We just want to understand the symmetries so we can talk about integrability. So if you want to make sense of this interaction, let's say the sigma in the XZ sector, which lowers an X to a Z. So take this X, right? And it wants to become a Z, right? There's a doublet, an X becomes a Z. Of course, the Z, by choice, somehow has to take either, you can define what this means, but we choose it so that when you're acting on an X, you preserve the first index. So here it's a first gauge group that you preserve. So if it's an X12, this should become a Z1. That's a convention. You could have chosen the opposite convention, but you have to choose one of them. So this X becomes a Z1. And now, of course, everything after that comes afterward on the chain, to make sense, you cannot contract a gauge group 1 index with a gauge group 2 index. That's impossible. So you need to convert everything after that to a gauge group 2. And for that, we need to introduce a coproduct. So maybe just quickly, even though, okay, I don't have time really, but maybe just to say that, okay, for the students, what is a coproduct? Now, if you remember that in your quantum mechanics, right, when you're looking at the total spin of two sides, you can write it, let's say, as a vector, the total spin of the first and the total spin of the second, right? And when you're acting on a state like up-down with the total spin, you can either act with this one, leaving the second one alone, or you can act with this one, leaving the first one alone. right? I think people are familiar with this. So this, instead of writing it in this way, we want to write it as, it's more convenient to write as a coproduct. So S times the identity plus identity times S, where this is again our spin generator of the algebra. And this indicates that this state lives in V times V. So it has the Hilbert space of the first spin, the Hilbert for the second spin, and this is the natural way to act on it. So this is what I mean by a Lie algebraic coproduct. It tells you how your generators, which are defined on a single site, so we know what, S, Z, let's say, acting on up, gives you H bar over 2 up, and so on. So these are defined as a single site. Now, the coproduct is what tells you how to move to 2 sites, and from then on to 3 and 4 sites. Right? So what we need to do clearly here, when you're acting with this sigma, which is your spin, basically, that lowers your X to a Z, your spin lowering operator, is to define an appropriate coproduct. And we choose this definition here, where we introduce this parameter gamma, or this operation gamma, which takes your xi to an xi plus 1, meaning that if this index is a 2, it's going to give you a 2 plus 1, but in a Z2 case, 2 plus 1 means 1. They're identified periodically. So this Z2 became a Z1. This Y21 got flipped to a Y12. So we want to define an algebra that has this as the correct coproduct and not this trivial Lie algebraic coproduct. Of course, only for the broken generators. For the unbroken ones, there's no reason to change our coproduct. So this is the structure we are defining. There are some details which, unfortunately, given I only have like 10 minutes left, I will skip. But to make this sensible, because as you can see, this operation is not gauge invariant, right? Because you can suppose this was a proper trace. Suppose there was another operator here, like a Y21, so that you can make a trace. When you do this, then this is not going to be a trace because that 1 would have become a 2. So we are breaking gauge invariance by doing this, but that's okay for now. We'll fix it. But we are fixing it for now. Well, we're dealing with it by opening up the trace. So now we're talking about gauge non-invariant operators, acting on them. And if you act twice with a broken generator, because each broken generator, gamma squared is 1, basically, for the Z2 case. If you act twice with a broken generator, then you go back to a trace-like state that you can close. So that's going to be our operation. Now, it's something that you cannot hit only once and preserve gauge invariance, but if you hit twice, you can. And acting on this, we can actually quite see relatively straightforwardly that the action, when I say action, I mean the Lagrangian of the theory, is invariant under this coproduct, appropriately extended to 3 and 4 sites, since the Lagrangian contains terms that are cubic or quartic in the fields. Maybe I'll just say a few words about the underlying mathematics here, because we need to understand this, is my claim, in order to really understand the symmetry and be able to work with them. So think of your standard group theory, right? You have a multiplication operation, and it takes 2 elements of the group to 1, but it works for every 2 elements. Any 2 elements of the group, I'm allowed to multiply them and get some third element. A groupoid is a generalization of that, where this composition of elements is a partial function, meaning that not every 2 elements can be composed. That's what this half arrow is supposed to mean. In practice, the way we deal with groupoids is a more kind of categorical kind of thinking, where you have your objects, you have your arrows, and you have structure maps. So if you have a bunch of objects, which are your group elements, let's say, and your composition tells you which of your elements are composable. And the rule is that if there's an arrow from one element to the other, then you can compose them. If this means the target and S means the source. So if the target of one group element is equal to the source of the other group element, then you can compose them. Otherwise, you cannot. So a groupoid with only one object is just a group. right? So all your, basically that means that all, sorry, the group elements are the arrows, right? So all your arrows from one object go back to the same object. So that means you can compose all of them. But if there are more than one objects, which will define what these objects are in a second, then this definition is more general than a group. There are going to be two kinds of groupoids that I'm going to be discussing here. Well, discussing is a strong word because I'll just briefly have the time to review them. If you look at this quiver, obviously this takes the structure of a groupoid, the way I've defined it, and maybe it's useful to make sense of the definition here. So remember, we had we had the objects and the arrows. Here I have two objects, which are my node 1 and my node 2, and I have a bunch of arrows. So if I want to, what do I mean by composition? I mean I want to follow to define a path on this quiver. So let's say I start with my with node 1. I can define my path as a combination of arrows that make sense, where the target of one arrow is the source of the second. So I can do a Z1, then I can do an X12 that will bring me here, then I can do a Y21, I can go here, a Y12, maybe a Z2. So any path that you can define here is by following the arrows is a valid path, and that corresponds to our gauge invariant operators in the gauge theory. So here the objects are our nodes and the fields are the arrows. Now there's nothing really special about this. Like, this is well known in the math literature that quivers are very strongly related to groupoids. What we want is something else. What we want is to be able to act on the fields themselves. So I want to be able to act on X and get Z. So I want to act on the arrows here. So now I want to define a new object where my objects are the arrows, and the arrows of this new construction are the generators of SU2, which are these for one side. So the raising, the lowering, the sigma Z, and the identity extending to the universal available algebra. Okay, I think I don't really have much time to discuss this construction in detail, but you need to split your SU2 into two parts. Yes? Oh, sorry, I thought there was a question.
I think that was background.
Oh, okay. All right, so you need to split your SU2 into two SU2s effectively, one labeled by 1 and 2, and the first SU2 acts on these ones, the second SU2 acts on these ones, back and forth. And that, okay, maybe sounds a bit trivial because what am I doing? I'm just doubling my SU2. But the moment you now start acting on two sides, you see you have to start mixing these generators because it's sigma 1 that can act. You know, this is now the coproduct. It's sigma 1 acting on X12, leaving, well, not leaving invariant X21, but making it into, oops, where am I here? Making an X12, or the other way around. And then here, when it acts on X21, you need the sigma 2. So you need to start combining these two objects kind of more non-trivially. So anyway, we kind of worked out this structure, and that's in the paper. I don't really want to go into a huge amount of detail into it, but it's an interesting new structure for how to define. Actually, what we are doing is not really at the level, even though I'm saying groupoid, we are really at the level of the algebroid, meaning the way that groups are related to algebras, groupoids are related to algebroids, meaning we're working infinitesimally. So the sigma is not an element of any groupoid, it's an element of the corresponding algebroid. By working like that, we were able to show invariance under this technically algebroid at the orbifold point. And it might lead us, I mentioned the Yangians earlier, it might lead us to be able to construct these Yangians that are underlying the integrability of the orbifold point, which are not known yet. We're also working on trying to formalize the structure. And for those of you who've seen a little bit of category theory, what this is a category where you have a category with objects and arrows, and then the arrows of the first category are the objects of the next category. And that structure is known as a two category. So we think that there is well, I'm not claiming that I'm very interested in category theory in general, but it might be useful in terms of constraining our structure to bring it to that formalism, and maybe mathematicians can help us. So we're discussing with some of the mathematicians, that might be able to give us some insight. Okay, I'm kind of out of time, so of course, so in the next maybe 3 or 4 minutes, I just want to say, of course, this was all at the orbital point. Now we want to introduce kappa in the game, so we want to move away from the orbital point, and we have a way of doing it using Drinfeld twists. But now what we're Drinfeld twisting is the groupoid. So this also defines new structures that were not really well known before, because normally you just you deform an algebra by Drinfeld twisting it. Here we have this more general structure, which is already quantum in some sense, and we need to deform it. But we wrote down suitable twists that I'm not really going to say much about. We can twist the coproducts appropriately. We have a way of figuring out what conditions these twists have to satisfy by looking at the quantum planes. Again, it's a bit of a long story to really go into the details, but based on that, we were able, for instance, to take the superpotential of the undeformed theory, or the orbital point theory, and write down the correct superpotential twisted to get the correct superpotential of the marginal deformed theory, and then with the appropriate twist, write a twisted coproduct for which the superpotential is invariant. So we are showing symmetry under an SU3 because we're doing it for all the generators, the XY, the XZ, and the YZ, and that's the full SU3. So the XY is fine, that's the unbroken symmetry, but remember the XZ and the YZ are these broken generators where now we have these groupoids and twisted groupoids. So we can do that, and we can also do it for the Lagrangian. Okay, it's way more complicated, and that probably took about 70 or 80% of the paper is concerned with doing the quartic terms and how to show invariance of the component Lagrangian. But we were able to kind of, with some tricks and maybe some assumptions that need to be better justified, show that the full Lagrangian of our theory is invariant under this twisted SU4 groupoid. And when I say invariant, okay, I mean it in a very special sense because everything we're doing here is in the planar limit. So, and of course the Lagrangian by itself doesn't know about the planar limit. That's something that comes from looking at Feynman diagrams. So what we kind of mean is that when we are acting with the generators, we are not allowing any operations which might break any of the traces in the Lagrangian and make them double trace. So that's something you don't need to do when you do normal SU2 or SU4 actions of the Lagrangian. Here we had to do it. So we're working kind of in the planar limit by making this extra assumption. What do we learn from this? Now, I'm hiding a lot of the technical work, but I can assure you it was quite a lot of technical work. And was it worthwhile doing this? Did we learn something by looking at the symmetries? I'm not going to read through this slide because there's a lot of information that I don't have time to explain. But the main thing you should keep in mind is the Hamiltonian of the theory does not commute with the scope product. So the multiplets that we make based on this co-product, you can write down multiplets and you can do, twisted groupoid representation theory of SU4, but the Hamiltonian does not necessarily respect that. So is that useful? Well, it turns out that you can still get quite a lot of mileage from these co-products. For instance, you can start looking at the BPS states, which are the states which have zero anomalous dimension, so they're protected. They don't get modified as you quantize the theory. You can relate them, using the appropriate twisted groupoid coproduct. You can take a state and act, and if you act twice, you can see this state is a closable state. The first index is the same as the last one. This one is not. The first index is the same is 1. This one is a 2. But if you act twice, you get this state, and this state is also a BPS state. So you can then you can take this. So take this, act twice, take the state, close it by putting a trace, and you can predict the BPS state. So this hidden symmetry that we are finding, this groupoid or twisted groupoid symmetry, actually has an impact on the spectrum of theory. It actually is still there to some extent. It's because it takes us from physical states to physical states with the correct anomalous dimensions. This is a very special example, admittedly. It's a bit harder to see this pattern in general, and that's something we're working with. Another example, again, also relatively simple, is the 20 prime representation. That those are the 20 states of length 2 that you can write. And we know how to write this twisted representation theory in this case. So how to relate all the states by moving within this multiplet, which is an SU4 multiplet, not an SU2 times SU2. But we can revive these broken generators, which are these blue ones, to work also in this case. Okay, I'm kind of done. So just to summarize, and then maybe we can ask questions. There's a lot of things that we I did not have time to discuss. How we do the Kornebithy ansatz, for instance. These results are kind of implied about how Ellie and her group, I was not involved in this research, but how Ellie and her group managed to solve the 3 and 4 Magnum scattering in the Z2 case. Also, their group have found some hints of integrability in the XY sector in terms of being able to construct higher conserved charges, which is another good test of integrability if you have higher charges in your system and you can show that they are conserved. We're working on this more categorical stuff, like formalizing the coproduct. There's also an interpretation, which I definitely do not have time to discuss, of mapping these spin chains to RSOS models, which are like like two-dimensional statistical models that is a very useful, interesting link, I think. We're doing the long length limit. I think there was a question last time about the Landau-Lifshitz limit of XXX. So we're trying to do the same now, like taking the Landau-Lifshitz limit of this alternating chain, where some results are already known from condensed matter motivations. So we're trying to take those results and apply them to this case. And hopefully we'll find something interesting, which can be thought of as describing some aspect of string theory in the dual background of the gauge theory. And okay, there's a lot more to do, but just to summarize what I discussed, or didn't have time to discuss because of the lack of time, I hope I convinced you that if you look at these n equals 2 orbifolds, these spin chains are dynamical. So the Hamiltonian is kind of dynamically determined at every site, and they have many interesting properties. And to understand them, we looked at the symmetry. And we found that these generators of SU4 can be upgraded to not be broken generators anymore, but now not of SU4. That's not possible because SU4 is a Lie algebra, but if you upgrade to a Lie algebroid instead. And I gave hopefully a few indications of what this Lie algebroid means or what it means for us in this case. And then once you've done that at the orbifold point, you can twist away and go away from the orbifold point and understand the marginal deformation as just this twisted, this effect of the Drinfeld twist on the orbifold point algebraic structure. So eventually what we were led to is this structure, which you can call a deformed or a twisted Lie algebroid. So, and maybe I will leave you with this, you know, it's perhaps nice to think of SU4, the standard Lie group SU4, as built on this quiver. Now, of course, here what you only see explicit is an SU3 because it's the Z and X and Y. But if you included on this quiver also the antiholomorphic one fields, you would see the SU4. Well, now we defined a algebraic structure related to this quiver, which you can call, I'm not sure if this is a standard notation or not, but the Z2 groupoid kappa deformed SU4. And we showed that our Lagrangian is invariant at the planar limit under this more general group. And of course, you can imagine you can generalize this to any other discrete group that you want to take the orbifold by and have a similar algebraic structure. We don't really know much about these things. We started studying the representation theory of these groups, these quantum groups, you could call them. but hopefully we'll have much more to say about them the more we look at them. Okay, I think I'll stop here. Thanks for your attention.
Right, fantastic. Any questions?
Are there
from the
any
audience?
questions?
I think I have perhaps a very vague question. So in sort of promoting your group to a groupoid, you've obviously made it more general. Have you lost any particularly important features? I guess is a question. If you move to a more general algebraic object, have you lost any group theorems?
Yes, I mean, of course, that is a fear that one always has, right? I mean, that's why, I mean, categories are very nice, but they're not very useful in general in physics. Because you lose too many features, right? And we don't want to go there, really. Although we think maybe, you know, our structure is rigid enough that we can still usefully, you know, get something useful out of the groupoid, out of the category thinking. But I mean, what we definitely lose here is, is the ability to act once, right? So in terms of the group, okay, first of all, in terms of group axioms, going to a groupoid doesn't really lose you very much, because you still have all the other properties that you might want. I mean, the compositions and associativity is still there, and all that for the groupoid. It's not there for the twisted groupoid, and that has been our main problem. So just going to the groupoid by itself. So before I started talking about the marginal deformation, before this point, everything here is nicely associative and has exactly the same, I would say, there's no real structure that's very different from the standard group. So we're not losing anything. The moment we come, apart from the fact that we cannot act twice. So act once. So if you want a gauge invariant operator, with your groupoid, you have to act twice to get another gauge invariant operator. So in a sense, we lose half our power. Like if you think in terms of creating a multiplet, but in terms of physical states, for the normal group, you can act once with a lowering operator, and you can still get a physical state. Here you have to act twice. Okay, so that's one defect. So we lost half the strength of our group. That's one thing. But before I turned on kappa, the structure was still associative. When I turned on kappa, unfortunately, we lose associativity. And much of the stuff I skipped had to do with how to live with non-associativity. And that, you could call it a major loss, I would say, because it's very hard to work with spin chains that are not associative. Some of the stuff I skipped here was understanding how to do that in a sense, and how to work in a setting that we call a dynamical kind of Jan Baxter setting and all that. But okay, I don't think I can do it justice now. So definitely we lost a lot. To me, these kinds of pictures show that we haven't lost everything, that we are still able to, and not only that, but also some of the results that Ellie has obtained, where they can actually write down like 3 Magnon wave functions. They look horrible. I mean, I must admit, they don't look very simple. They're not like the usual Bethe approach. However, it's kind of possible to do that. And probably the reason that's possible is because of this additional symmetry. I cannot justify this statement at this point because we haven't studied yet how the symmetry interplays with the coordinate Bethe ansatz, but it should be there. It should be telling us something about how your magnons also interact. So yeah, and I think that's where one of the things we're going to, like, to, you know, if the symmetry, well, the symmetry is there, but whether it is useful, as I was saying here, it goes back to your question, have we lost too much by doing this generalization? And I'm not sure I can say we're hopeful that we've kept some interesting structure, because we are getting like some kind of selection rules. We're getting some, you know, you can probably promote this to also the quantum level. You can probably write down Ward identities for these deformed symmetries. That's what I kind of implied here, groupoid conservation laws. Like there is another theorem for groupoids, for instance. these Lie groupoids have another theorem, and that's important for physics. If you do not have the other theorem, I would say, okay, you've lost too much. But we can define conservation laws. And that's one thing that we hope might also be present at the quantum level. And that might really give us something useful from this symmetry.
Thank you very much.
Thank you. Now you also answered my question. Yeah, about Newton, about conservation. That's
Sorry, what was the question about the
conservation laws? I mean, that is really the key thing, right? Otherwise symmetry considerations become not very physics relevant in a sense if they don't.
Yeah,
exactly. So we of course are physicists, and we don't want to get lost in category theory. We want to do things that somehow lead to interesting physical observables, and it's very nice to see. But there are papers. If somebody's interested, they can write to me. I can give you some literature on how these Lie groupoids still satisfy conservation laws. So in general, I think many papers that one reads about groupoids, and I'm not an expert by any means on groupoids, but many mathematicians are pushing for groupoids to really be taught at the same level as groups, because they are really not that different. You really don't lose very much by generalizing to groupoids and just having this partial composition law instead of the full composition law. So it is hopefully that implies that we can really use these for something. Hopefully in a couple of years I can come back and tell you what that something is. Yeah.
Very good.
You also answered my question about the literature.
Okay, yeah, if somebody wants to know a little bit more about groupoids, okay, you can look at our paper, of course, the one I mentioned at the start, but so we give some references to some general introductions to groupoids, but some of these stuff about conservation laws and the proof of Noether's theorem haven't really been, I'm not sure we cited them specifically, but we're looking at them, and they seem to be quite reasonable results that we're hoping to use. Yeah.
Yeah, so maybe two questions. So following up on these groupoids, and as Herbert knows intimately well, groups are probably the most fundamental and important objects in physics. And I'm not being facetious. I mean, it really is, especially when you consider that ultimately symmetry is what drives all of physics, and symmetry is represented in physics with groups, and then it's a representation theory of groups that then drives everything in field theory, which is what describes the world that we see around us. So I guess since I wasn't going to ask this, but you're sort of saying that you don't lose much with groupoids and they're very similar to groups. Is there something that, this is not a very well posed question, but I guess, is there some way that we could reformulate basically all of symmetries and observables in terms of groupoids? And what does that potentially get us when we think about it at the level of, say, Wigner's theorem, or the representation theory of the fields that go into the Lagrangians that form the basis of field theories?
Yeah. Okay. I mean, of course, I won't want to be overambitious at this point, because so it's important to say that, of course, we are not modifying any of our Lorentz algebra, right? I mean, we still have the usual Lorentz and Poincaré group and all that, right? So our fields are just normal scalar fields and spinors, right? And I consciously avoid working with non-commutative kind of field theory so this is not non-commutative field theory. This structure is only in the internal space. So it's only the R symmetry which rotates the scalar that's become a groupoid, right? So everything that you know about field theory works perfectly fine here, but I'm just saying that there's perhaps some additional knowledge that you can get if you know that, for instance, there is this representation of the groupoid, which is still there, even though you don't have an SU4, but you have the groupoid SU4. So this is basically representations of your internal symmetry group, not of your scalars, of your Lorentz group. So what we can get. Okay, so the main motivation that people give for groupoids is, like for instance, consider this page, right, or some page, right? There's an obvious symmetry here, which is that you can translate by 1 centimeter upwards the whole page, right? Like this, you can go from here to here, and then from here to here, right? That's a translation symmetry.
Yeah.
Obviously, this is not true. There is no group that does it because the page stops here. Right. So translation symmetry is not a true symmetry of this page, even though obviously there is some symmetry that you can see here, but it's not really, there's no group because translation symmetry stops. But you can find a groupoid version of translation symmetry which does this. So the groupoids are often used in contexts where people want to say, well, look, there's a pattern of tiles. Okay, this is not really directly our setting, but there's a pattern of tiles on the floor. Obviously, it's very symmetric. As physicists, we would like to be able to describe the symmetry of this pattern of tiles, but the room is finite. So there must be some way of describing what happens when you reach the end of, like, what happens to your group element, and why is that group element nilpotent at the last step? And the language of groupoids allows you to do that. Okay, so it's again, it's a very different context from mine. I mean, we're doing Lie groupoids, and it's a bit different from what I'm saying, but I'm hoping that something similar can be there. That there are contexts where actually group theory is nice if you work locally somehow, but it misses somehow some picture if you want to take it seriously, right? And yeah,
super interesting because actually something that I'm actively working on is thinking about looking at just even a classical problem, Hamilton's principle, where you have a start and you have an end, and doing it on a computer, which has when you discretize, as a finite size grid, and you want to have your conservation of energy, you want to have your conservation of momentum and rotations and boosts, but you are stymied by the finite sizedness of the thing. So that's really, really interesting.
To me, it seems very relevant. I mean, I can send you a reference or two about what I'm talking about, the tiles. Of course, that is probably like discrete versions of the groupoids that I'm talking about here. Here, I want continuous groupoids, so it's a little bit different. But I think people do study these kinds of. That's one of the motivations for groupoids, like to be able to work with these situations where obviously there's a symmetry, but groups by themselves are not powerful enough to show this symmetry. In our case, what they're not powerful enough is to deal with generators that are, that want to link this field to that field. Let's say because they're different gauge groups. Okay, so group theory can never take this X to this Z in this context, but the groupoid can. So that's our motivation for extending it. But I'm sure there's other motivations, and finite systems are often touted as a good motivation for looking at groupoids.
I mean, following up on that question, then, could you think about this as some way to get beyond the Coleman medulla no-go theorem?
Again, we're not modifying. We're not introducing a
groupoid. I keep pushing you away from what you're talking about.
We're not introducing a groupoid in the space-time directions, right? So we still have flat space, and well, we have the conformal group, which already violates Coleman medulla in a sense, right? Because there's no S matrix. Okay, we are in a conformal theory, but and we have supersymmetry, which also is a violation. So we've already kind of torn down Coleman medulla here, but in multiple ways. But I'm not trying to. Of course, I think it's possible. I mean, if you were to move away, because I think Coleman medulla do assume groups. It's a group, and being a supergroup already violated that. Now we're saying, suppose you wanted to go to some groupoid version of Poincare symmetry, then probably that would also give you a nice loophole. But we're not really, at least in this work, we're not trying to exploit that because we are doing standard field theory. There's nothing non-commutative in the field theory, but there's additional symmetry, is what our point is. Which you might want to use this additional symmetry and make some progress, or you might, I mean, you can live your life ignoring the symmetry, and then you might just be seeing some patterns. Oh, these two fields seem to, have an energy related by something, and you might not be able to explain that, but this symmetry might give a good explanation for that, like for patterns or structure in the spectrum, let's say, that you might not otherwise be able to explain.
Fantastic, thank you.
But granted, I mean, it's a very special theory. I mean, it's n equals 2 supersymmetric and not even the most general n equals 2. So, you know, there is quite a lot to do to make this like a practical statement about any field theory or whatever. This is like a very specific context at this point.
Yeah, but it's a fun thing to play.
Yeah.
Yeah, it is fun. I mean, I must admit that the non-associative stuff is not fun. The one I skipped. So again, if you look at our paper, it's maybe a, I don't know, 60, 70 page paper. Probably about 40 of those pages are dealing with the non-associativity, and that's going to be a bit painful. So I'm not sure how much mileage you can get there. But at the orbifold point, of course, I think it's very beautiful and clean, and everything works really well.
Very good. Question?
Yeah, I think so.
Right. Well, thank you, I would say.
Yeah, thank you very much.
Okay, thanks a lot for inviting me. It was really a pleasure to present.